Hello there, hope you guys are doing well in current lockdown, that you're staying busy with some of the distance learning stuff and that you're having a good go with the questions on things like Seneca as well. All right. So in today's session, we're going to be looking at chemical interactions. It is stuff you have previously covered, and there's a little bit of new knowledge in here as well, just to kind of get you guys thinking about future things. At the end of this PowerPoint, there'll be a little slide that directs you towards an online resource called Educake. You may or may not be aware of that, but there are a few questions on there that test you on some of the knowledge in this PowerPoint. All right, so there's a lot of important information in here to help you answer those questions. Okay, so let's go and have a look at some of the stuff we'll be looking at today. So to start with, this will be familiar to you, a bit of a do now, just to kind of have a think about some of the questions and some of the previous knowledge that I won't really be covering in this topic. All right, so some stuff based on the periodic table and some things like how to read the periodic table. If you've not got a periodic table on you, which you should do, you should have your planners still, just Google periodic table and have a look with some of those questions. All right, so pause the video or whatever you need to do now, take your time with those questions. The answers are on the next slide for you. Well, okay, so take a couple of seconds or a minute or two just to have a look at that. So this will be stuff that you should absolutely be familiar with. All right, so the structure of the atom is stuff that's been covered in the last year, in year 7, and has been covered this year in year 8 as well. But there's going to be a little bit of a recap on it, just to kind of refresh your brains to make sure you're aware of what I'm actually talking about today. So when we're talking about atoms, we're talking about the smallest stable substance that we can kind of get down to. All right, so they're the building blocks of the universe. Everything, including you, is made up of atoms and of elements, and there's 100 or so different types. All right, approximately 100, I think in total, 118 different types of elements. You'll have heard of them. Things like oxygen, calcium, hydrogen are all things that you'll find in your periodic table of elements. All right. Now, something that some people sometimes get confused on is that word I've highlighted there, subatomic particles. We're basically just talking about the 3 parts of an atom that you need to know for your exams. All right, this stuff comes up in your exams. It's really simple 1-mark questions, so it's important that we're getting these things nailed down now. All right, now I've prepared a lovely diagram for you there on the right. I've given it a key as well to kind of show you what parts we're talking about if you're not quite familiar. All right, so we often draw electrons as crosses, and we try and do a bit of a difference between our protons and our neutrons. So for example, my protons are just blank and my neutrons have been shaded in. The 3 particles that I've already mentioned are electrons, protons, and neutrons. Okay, now for this topic, for this kind of PowerPoint that you've got today, I'm only really focusing on the electrons. Okay, protons and neutrons are important, but when we're talking about reactions, we are normally talking about electrons. Okay, so continuing our conversation on electrons, we do need to understand the electron configuration within different atoms. Okay, now this is again stuff that we've kind of covered before, but we normally talk about the first 3 shells. We should know that the first shell can only hold 2 electrons. The fancy word they often use with this is capacity. So the first shell only has a capacity for 2 electrons. Your second and third shells, as you'll see written on there on the left, have a capacity for 8 maximum. If you have more than that, say for example, I've got an extra electron, I've got a 9th electron, it'll have to go on the next shell. You'll create a whole extra shell for that electron to kind of live on. Okay, now I've given chlorine as an example. I've got the electron configuration there with the dots, and I've also got the card that you would find on the periodic table, right? The number 35 and the number 17. Okay, now in the case of chlorine, we know that there are 17 electrons. That is always equal to the smaller of the 2 numbers, the atomic number. Now sometimes, depending on the periodic table, that atomic number can be at the top or at the bottom, but all you have to remember is that it's the smallest number on there. Okay, the atomic number is the smallest number. Now the electrons is normally always the same as that, so I know just from looking at that card, looking at the smallest number on there, 17, there are 17 electrons. Now to organise this, to put it into the electron configuration, I just follow the rules that are at the top there. So I can only put 2 electrons in the first shell. So out of 17, 2 of them are in the first shell. I then can only put 8 on the second shell because that's the maximum capacity that it has. If I then look at how many electrons I've got left over, I started with 17, 2 on the first shell, 8 on the second shell, 7 are left to go on that third shell. All right, so it's not filled. There are 7 electrons on that third shell. And to double check that everything adds up completely, I'll add them up at the end. Okay, so 2, 8, and 7. If you add those up together quickly, that'll equal 17. So my maths works out there. Okay, I've correctly put that configuration on. If you look at the diagram just up there, you can kind of see that as well. Okay, so if you count all those electrons up, there are 17 in total. There are 7 in that outside shell. Now I mentioned just then that third and final shell is not completely full. There are 7 in total, but we know that we can hold 8 on our third shell if we look at our bullet points on the top left there. Okay. Now naturally, most elements are just unstable. They've not got a full outer shell, so they're unstable. The only group that is stable is group 0. They are naturally stable because they already have a full outer shell. So if you look at things like helium, argon, stuff like that, they are our noble gases. You'll have heard that as well, but they're already stable. In order for an element to become stable, it'll have to fill that outer shell. Now that can either be done through losing electrons or sometimes through gaining electrons as well. So for example, chlorine will gain an electron because it's easier to gain that extra one. Okay. So we talked about electron configuration of atoms. We're going to talk about now some different compounds of and their electron configuration. So you'll notice on the screen there we've got H2O, which is made up of hydrogen and oxygen. Now if we start looking at the left hand side there, you'll notice that hydrogen only needs 1 more electron to fill that first shell. So if you look back at the previous slide, we said that the first shell has a maximum capacity for 2. Hydrogen only has 1, it needs 1 more for that full shell. If we look at oxygen, it's got 2 shells, but that second shell is not full yet. We should know that it can have a maximum capacity for 8. It needs 2 more to fill that shell. It's got 6, needs 2 more to make 8. Now if I combine oxygen and hydrogen together, so I've got 1 hydrogen, 1 oxygen, hydrogen's fine because it can share an electron with oxygen, but oxygen still has 1 more electron to fill the outer shell. So what we end up with is H2O, water, 2 hydrogens and an oxygen chemically bonded together, sharing those electrons through something called a covalent bond. Okay. Now you'll notice on the diagram there, it always looks like Mickey Mouse to me, which is kind of the way that I remember it and helps me remember it in tests and exams and stuff. There will be some questions that ask you to either identify the correct ones. Okay, so these next couple of slides will help you with some of the questions, definitely. You can see that the hydrogen is sharing 1 of its electrons with oxygen, and they're kind of on the same line next to each other. Okay, so we can kind of tell straight away the configuration of H2O. So another common compound that they might ask you for the configuration of is carbon dioxide, so CO2. It's a compound you'll all have heard of. And we're still talking about oxygen, so it needs 2 more electrons to fill that outer shell. But when looking at carbon, it needs 4 more. So if I just have 1 oxygen and 1 carbon, and I join them together and they share those electrons, carbon will still need another 2 electrons. Okay, so what we end up with is 1 carbon covalently bonded to 2 oxygens. And again, similar to our H2O example earlier on, you can see that the electrons are being shared on the same line. Our carbon electrons are represented by crosses, so you can see where they've come from. And our oxygen electrons are represented by the shaded in circles, okay, or the dots. You can see where the electrons are shared from and who is sharing those electrons. Okay, so a really simple diagram to represent how the electrons and how the covalent bond is structured. Now, often you will find chlorine combined to another chlorine to form a molecule. Okay, so not quite a compound, but a chlorine molecule, so Cl2. Now, chlorine only needs 1 more electron to fill that outer shell. If you count them up, you'll know that there are 7, and we know that we can fit 8 in total. So an easy way to fix this for chlorine to become stable is just to join up with another chlorine, and you end up with my diagram on the right over there. You can see that through the overlap, they're sharing some electrons. The cross is coming from one of our crossed chlorine, and the dots or circles coming from the other chlorine. So it's showing you exactly where they have come from. It's a common diagram that you can sometimes be asked to draw in an exam. However, they do give you the circles. They'll just ask you to add on the dots and crosses. All right, so they're not the most difficult of questions to do, but one that requires you to make sure you know the electron configuration. Okay, so we know that chlorine has 7. It can easily share one of those electrons with another chlorine, so that they've both now got a full outer shell. So similar to our chlorine molecule, you can also end up with hydrogen molecules as well, so H2. Now we know that hydrogen only needs one more electron for that full outer shell, so they combine with each other quite nicely, quite easily. Okay, and again, you get our overlap diagram over there, our dot and cross diagram, where they're sharing those electrons. It's quite a bare diagram. There's not a lot on it really, just because hydrogen only has one electron to share in the first place. All right, so a H2 molecule is just those cross and dot in that overlap between the two molecules. Right, it's important that you try and have that overlap if you are asked to draw them, okay, or at least place your crosses and dots within the overlap of any diagrams. Okay, so the last example of a electron configuration we're going to look at today is hydrogen chloride. So a hydrogen and a chlorine atom covalently bonded together. We've discussed these two elements already, but they both only need one more electron for their full outer shell. So it's quite easy for those two elements or those two atoms to combine together covalently and share those electrons. As always, we try and represent where the electrons have come from. So if we look at our diagram on the right hand side there, the chlorine electrons are drawn as circles or as dots. The hydrogens is drawn as a cross. So you know exactly where those electrons are being shared and with who. Okay, so for more complex diagrams, this becomes really important, so you can see exactly where electrons have come from. But for diagrams like this, it's quite a simple cross and a dot. That's the last one we're going to look at. There will be some questions on this, but we're going to move on to a slightly different side of this topic now. So we've talked about how electrons move around in electron configuration diagrams. We're actually going to talk about now some of the different types of reactions that you are expected to be familiar with, and some of them you will be familiar with anyway. So the 3 we're going to look at today are combustion reactions, reactions that involve rusting, and a little bit more information on those, and then reactions known as displacement reactions. We're going to give you some information on those, and again, there will be questions on EDUCATE that will test you on your knowledge from these. Okay. Starting with combustion reactions. A combustion reaction is a chemical reaction involving a fuel and oxygen. So oxygen is the important part there. Now, when talking about combustion reactions, the common one that people think about is things like flame and fire and burning fuels. So when we burn fuels, we do that for normally 2 reasons. The first one is for the heat that comes off a combustion reaction. We use that for things like warming up our homes, and for cooking foods and stuff like that, and for also powering power plants and power stations. The one that people sometimes forget about is that we burn fuel sometimes for light as well. Now, there are many examples of combustion reactions, for example, burning woods or burning fuels like petrol. But even the use of a Bunsen burner involves combustion, so something you'll all be familiar with. There are 2 types of combustion reactions. There are complete and incomplete combustions, and we're going to look at each of those in a bit more detail now. Complete combustion occurs when there is enough oxygen to completely use up all the reactants. So if we burn a fuel, if we've burnt up all of the fuel and there is enough oxygen for the entire time that we're burning it, then it will be complete combustion. Now, when we use things like Bunsen burners, the combustion, to show that complete combustion is happening, is the flame will be a nice bright blue colour. Okay, so when we open up the air hole, so it's completely open, we're making sure that there is plenty of oxygen to burn all of the fuel at the same time. Okay, so it means that everything's being burnt and used up completely. So when we do this, we'll have our fuel, which could be something like methane. We'll have oxygen in there as well, and they will react together to form things like carbon dioxide and any other products as well. All right. However, with incomplete combustion, that means that there is not enough oxygen, which can often lead to things like smoke being produced. Now, it also can leave a black residue, something that's often called soot. All right, so you might see this on things like candles. If you burn a candle, you might notice that around the edge you'll get kind of like this black residue, this soot that's left over at the end. Okay, now because there is not enough oxygen for this combustion reaction, it can also produce a toxic gas called carbon monoxide that is different to carbon dioxide. Carbon monoxide is toxic, it can be fatal. Now, we can demonstrate this with something like a Bunsen burner. So that diagram there is a good example. That yellow flame will be producing a small amount of carbon monoxide, not enough to cause us any harm. But everyone in their homes near your boilers should have a carbon monoxide alarm, because you can't smell carbon monoxide, you can't taste it, and you don't know you're under the effects of it. So it can make you feel really dizzy, really poorly. So the alarms near your boilers are really important. So incomplete combustion can be quite a dangerous combustion, one that you need to be really careful of when you're around it. So some combustion reactions aren't as exciting as things like burning flames and explosions and all that kind of jazz. Rusting or oxidation is a type of combustion because it involves water. It involves water and oxygen. So metal like iron left in contact with oxygen can result in this rust being formed, okay, and it will change the way that the metal behaves. So if something starts rusting, it'll tend to flake off and break and becomes quite brittle and easy to damage. Obviously something that you don't want when you're building your boats and your ships, okay. Now, one easy way to prevent something like rust from happening is by covering it up. So often they will paint a boat or paint something metal so that it doesn't have contact with oxygen, or perhaps just covering it up with some plastic or a rubber coating. This means that you're not letting the oxygen actually get in contact with your metal, such as iron, and if you can't get in contact with it, it can't then oxidize and then rust. So rust is an example of a combustion reaction. It is one that there might be one or two questions on as well. The last type of reactions we are going to look at or talk about are these reactions called displacement reactions. So many reactions occur between compounds that already exist. In a displacement reaction, if we have a more reactive metal, it can actually remove the metal from the compound and take its place. Okay, so kind of replaces it. Fancy word for that is displacement. If you've been displaced, you've been removed or moved out of the way. If we use something like a reactivity series, so that diagram that's on the right just over there, we can actually predict the products of a reaction or a displacement reaction. Now, there's a long list there of different elements. The more reactive it is, the higher up the list it is. So for example, potassium is our most reactive metal on that series. Gold is right at the bottom there. We also have two non-metals in there, so carbon and hydrogen. So they are kind of reactive, but they're in a bit of a list there with all the others. So for example, magnesium is much more reactive than copper. Okay, so if we have something like a copper compound, the magnesium would take its place. And I've got an example for you now. Keeping with our example of magnesium and copper, if I have a compound of copper oxide, so copper and oxygen combined together, and then I add some magnesium to that compound, because magnesium is higher up our list, higher up our reactivity series, it will displace copper, it will remove it from there. And instead what you'll end up with is magnesium oxide, and copper will be left all on its own. Now this can be really useful for certain elements if we want to be able to get hold of them. So for example, iron oxide is not that useful. We mentioned it when we were talking about rusting. It's quite brittle, easily breaks, and is often how you will find iron in the natural environment. So iron is normally found in an ore as iron oxide. I don't want that though. I want iron just on its own to make tools and all other kind of things. What I can use is something higher up the reactivity series to take its place. So often we'll use something like carbon. Because carbon is more reactive than iron, it will kick it out, it will displace it from iron oxide and become carbon dioxide instead. We're left then with pure iron all on its own, and we can actually then start using that for making tools or making vehicles or all other kind of stuff, important stuff, whereas iron oxide would have been useless. So displacement reactions are really important. They allow us to get hold of elements that are quite difficult to separate from their compounds. Now, this reactivity series is important. It's often worth trying to memorize it. Now, that's quite difficult. So you'll notice on there's an example of how someone's tried to order it and come up with a bit of a song or a phrase to help them memorize it. It might be worth, while you've got your free time from your distance learning and stuff, trying to come up with your own method of memorizing this reactivity series. So come up with your own kind of phrase, your own kind of sentence or song that will help you memorize all of those elements in the correct order. The last topic that we're going to talk about is this idea of rates of reaction. Now, reactions happen at different speeds. Some are much faster than others, but we can measure how quickly they happen. We call this rate of reaction. So we can increase the rate of reaction, we can make it faster, and sometimes we can make it slower as well. Okay, so rate of reaction, how fast is our reaction happening? Now, there are two ways that this can be measured. The first one is how long does it take for our reactants to be used up? So if I mix or if I react two different chemicals together, how long does it take for those reactants to disappear or to be used up? The second method is looking at how long it takes for a certain amount of products to be made. Okay, so you could be looking at how much gas is produced and time and see how long it takes to reach a certain amount. And that is another way of identifying how quickly a reaction is happening. Now, we mentioned increasing the rate of reaction, so making a reaction faster. There are 4 ways that that can be achieved. So we can increase the concentration. So if I have more reactants, so for example, if I'm using acid, if I have a higher concentration acid, or if I add in more oxygen to a reaction, I'm increasing the concentration. If there are more reactants, it theoretically should happen a lot quicker. We can also increase the temperature. Now, we've discussed this in year 8 and a little bit in year 7. Temperature is just particles vibrating. So if I make them vibrate quicker or move faster, they're going to react together much more quickly. They'll collide into each other and form a reaction. I can also increase the surface area. If there's a larger surface area, it means that more of the reactants can react together at the same time. So it increases how fast these reactants are reacting together. I can also make sure that there is a catalyst present as well. So a catalyst will speed up a reaction just by being there, but it does not get used up itself. All right, so catalysts are really useful for making reactions a lot quicker. Now, that is kind of the last of the stuff that I want to talk about today. I'm going to finish off with one last slide for you. Now, I have been saying throughout this PowerPoint that there will be questions on EduCake for you guys to have a go at. It will kind of test your knowledge gained from this PowerPoint. All right. Now, all of those questions, there is an answer for them within this kind of PowerPoint, within this information. So feel free to go back through it to try and help you with some of those questions. I hope that you guys are staying safe and sensible during the current climate with quarantine, and I hope that you are getting on with your distance learning to keep you guys in the know and keep revising that key content that we have covered. Thank you very much for your time.